March 2020, a global pandemic swept the world and a lot of things changed about the way we live and work. Offices emptied out as employees began working from home. Schools were empty as students started e-learning from home. Even doctor visits went online for all but the most critical of needs. And with this, the household battle for bandwidth began. So the result? Soaring broadband consumption. 2.7 billion minutes of Microsoft Teams meetings in one day, 300 million daily Zoom meeting participants, and every minute of every day, 500 hours of video are uploaded to YouTube according to these sources. This is soaring broadband consumption, especially in the upstream. According to OpenVault, upstream consumption has spiked 56% year over year, and it shows no signs of fading per NCTA data that shows it roughly leveling off even up through current times. So, cable operators have responded to this challenge. One North American operator was quoted saying that they've completed all planned 2020 node splits by mid-April, so splitting nodes was our go-to method to keep up with this demand. But our old tricks are reaching their limits. Business as usual node splits are challenging because our hubs are overflowing. We don't have the rack space, the power and cooling, and we can't afford the cost to keep doing things the way we have. Getting more bits per hertz going 16 to 64 QAM is challenging because in much of the world we're already at 64 QAM.
Sounds good.
And filling empty spectrum with more carriers, there's no such thing as empty spectrum except the garbage band in most of the world today. But fortunately, new methods are available. We can do node splits using the techniques in distributed access architectures. We can get more bits out of the hertz of spectrum we have with OFDMA, and we can get more carriers by changing to a mid-split or a high-split architecture. So which of these is the preferred challenge? Which is the right answer? Well, the answer is most often some combination of these. There is no one right answer. It's usually a combination. But each of these options has their challenges. If you want to use distributed access architecture, there's challenges with maintaining and troubleshooting the network. PTP timing suddenly matters. Video's not created until it's out at the remote PHY node, so verifying you have the correct programs in place.
Hey, Evan, you have some audio.
If you go with the mid-split or even the high split, all of a sudden you may have the FM band as part of your upstream. You can imagine the challenges that creates. And FCC proofs, how do you do that in the United States if 138 megahertz is now on your upstream? And even OFDMA has its challenges. How do you see upstream ingress through the seemingly always-on OFDMA carriers? How do you manage the complexity of all the different network equipment manufacturers and all of the different types of architectures that a technician may have to work on in a given day? These challenges become even more daunting when you combine multiple of these options into your network. But at VIAVI, we've been working on this for a long time. Let us help you enable a seamless transition to the advanced upstream. Through our decades of HFC experience, our complete end-to-end solutions covering your entire network, and an agnostic, NEM-neutral approach that allows you to mix and match pieces from different vendors and not have any of the operational challenges that you would otherwise have with siloed systems. So, for more information or to schedule a demonstration, please request a meeting with one of our subject matter experts. Remote and virtual tests are not new concepts, but they're getting a lot more attention lately as seemingly overnight, service providers globally have had to come up with initiatives to minimize risk for technicians and subscribers alike. This includes enabling all technicians, including new technicians, to complete jobs right the first time, especially when these jobs involve entry into a customer's home and business. We've heard "stay safe is the new save money" as a mantra, and while safety is the utmost of criticality right now, it is important that we cost-effectively are able to get and keep customers connected to increasingly critical broadband services. But there are new considerations and new constraints to achieving this goal. And one is entry into customers' homes and businesses. This is generally prohibited in a lot of the world, and where it is allowed, there are a lot of limitations on who can enter and when. This has spawned the development of a lot of tools for technicians to remotely turn up new services and remotely troubleshoot these services from afar, sometimes using tools like augmented reality. When entry into a home is required and allowed, then being able to get in, fix it right, and get out quickly is extremely important. And tools that help you do this are also getting a lot of attention, again, to minimize risk for the technician and the customer. We can't forget about our maintenance techs and our field technicians who, while they don't enter businesses and homes as often, do come into contact with a lot of people, especially in dense urban environments. So coming up with zero-touch and remote maintenance capabilities for these technicians is also critical. And the last thing to consider is some of the services that are now being used over our broadband pipes more than they have in the past. An example of this is VPN. With a lot of people working from home, VPN usage has skyrocketed, and these VPN services are generally not provided by the broadband service provider. Despite this, we know that the broadband service providers are generally guilty until proven innocent.
Hi, my name is Juan Castro, and welcome to another session for VIAVI DOCSIS 3.1 OFDM Basics. Me, myself, and Dave Dolnick will be presented today as solutions engineers.
Hello, my name is Dave Dolnick from VIAVI Solutions, and I'll be joining my colleague Juan Castro from the West Coast and talking about OFDM DOCSIS 3.1 technology.
All right, here's the table of contents, the agenda, the network variations. We're going to review some of those concepts. We're going to talk about single QAM carrier, the methodology of DOCSIS 3.1. Yeah, so here's the table of contents, the agenda, network variations, single QAM carrier, the methodology of DOCSIS 3.1, and then we're going to be talking about the components, the PLC, the next core pointer, testing the OFDM setting levels, and all of that goes with 3.1, the service layer testing as well. The objective is to understand the DOCSIS overview of the difference between a single QAM carrier and a DOCSIS 3.1, the building blocks of testing OFDM, using the profiles analysis, and deploying OFDMA and the return path. Let's talk a little bit about the network, an HFC versus a DAA infrastructure. Here's an example. On the top, we have the example of traditional HFC network. This is an example of showing the RPD, as most systems are starting to deploy the RPD in a traditional optical node. Some systems have a combination of both 5G, remote LT, the business services, as well as the traditional optical node and remote PHY. So the networks vary in the way the infrastructure may be, and testing will be accordingly. All right. From a downstream bandwidth, from a DOCSIS 3.1, DOCSIS 3.1 will support anything on the upstream from 5 to 204 megahertz. The downstream all the way out to literally 1.2 or 1.7 in the future. All right. So all of these features are starting to change already as networks are deploying not only 5 to 42, 65, 85, and as well as 204 megahertz. All right. So North America, as opposed to the European systems who already deployed some of these features. Here's just an example of the downstream. When we look at the downstream, for example, we could see DOCSIS. We went from analog to digital, and we went from analog to digital to single QAM carriers, as well as OFDM carriers, for example. All right, and now I am starting to work with systems who are deploying nothing but DOCSIS carriers and no more digital video carriers themselves. So the network will vary based on what they've deployed. As well as for the upstream. We went from SP, for example, single QAM carriers to obviously carriers used for the set-top boxes, as well as to the deployment of an OFDM carrier, including the exclusion zones. So the systems will vary in bandwidth on the upstream, as well as the downstream, as well as the variations of all the different types of carriers that we may be utilizing. test locations. All right, so testing the entire network will be different, right? In this first example is our head end. All right, so head end, depending on a traditional HFC, we can verify all of the RF testing, whether the head end or hub. We can do the same thing for the legacy optical nodes. So the head end or hub, the HFC, or the home and the business, everything will vary according to, we want to verify the downstream and upstream bonding, as well as the throughput required at all the locations, so we make sure that we maximize the service across the entire network. When we talk about testing the network on a single QAM carrier, for example, we verify level, pre and post bit error rate, echo, group delay, in-channel frequency response issues. When we talk about an OFDM type of carrier, we're basically doing the exact same thing. The difference is now we're adding correctable and uncorrectable code word errors. So the variations across the network, whether we're at the residential, testing at the tap, the ground block, or the CPE, through the infrastructure of the network, or back at the head end. Again, there will be variable different types of tests based on a remote PHY network, which basically is the same concept, or testing back at the CCAP, right? Which at this point is basically we're testing at the packet level. So there's variations at the RF, or basically for a DAA network. So the variations will be different based on the infrastructure of the network. Okay, so let's start with the basic concepts. First is a single QAM carrier, basic measurements. All right, it's things that you already done and are currently doing. On this example, we're using the ONX, and we're verifying all of the traditional measurements, which includes the level and the MER across the entire broadband. All right, we verify the level, the MER, the pre and the post bit array. We also verify something new to most fulfillment, which includes the echo, the group delay, and the ICFR. We're also verifying DQI across the band. All right, so we're going to verify and then verify the level and the MER and compare that against an OFDM carrier as we continue. So today's meter, like the ONX, is able to verify everything for you at one. Well, instead of doing like we did with the legacy DSAM as opposed to a single QAM carrier, we're trying to verify the entire broadband for you. We'll verify other things. Other things that we're going to verify locally too is we want to verify Ingress. Like we want to, when we do the residential, whether it's the ground block or even at the tap, we want to verify that the Ingress is being suppressed at the home. Generally, the setting is at -30. Just like we verify Ingress on the downstream, the ONX has the ability to look at the spectrum with Ingress, and we want to verify Ingress in certain areas. So the meter can be set up to verify Ingress, like this example is 700, 800, and 900 megahertz, to make sure that it meets the requirements for future deployments of other carriers in that specific range frequency. All right. We want to verify frequency response, so we want to use Smart Scan to verify the entire broadband, make sure that we meet that peak to valley. Like maintenance technicians to verify the network, for example, to verify sweep, we're using, in this case, we're using the carriers to verify the response of the network. We're also verifying any level variations over time, depending on the type of carrier or the carrier that you're locked in. We want to verify the in-channel frequency response of every single carrier across the band. Anything in green passes, anything in red will fail. All right. So the meter itself is verifying every single carrier across the band. From an MER perspective, we have an independent analysis across the entire broadband for each individual single QAM carrier, for example. So we can verify both the MER as well as the BER as well, okay? We also verify any MER over time. So if there's if you're on a specific carrier, any variations on that particular carrier affected by any other sources that they may affect the MER. DQI as well, just in case there's any variations in amplitude or noise or anything that can impact the DQI. Each test is verified different types of scenarios that could impact a single QAM carrier. All right. So a DOCSIS 3.0, so what we can do is a one check. The one check is a one test, automatically verifies both the upstream ingress, again, at each location, whether the tap, the ground block, or the CPE. We also have an ingress expert for the network, so they can verify whether it be at the head end or be at the network, at the optical node, or the trunk amplifier, line extender, etc., or the TAP. All right. In this case, we're verifying the Ingress, we're verifying the entire downstream, we're verifying DOCSIS, bonding verification across the band, and then we're going to use the session expert, at least from this case, in this example, the TAP or the ground block or the CPE, in order to qualify the entire job that we'll be working on. So there's quite a bit of information being captured on both the upstream or the downstream. The DOCSIS measurement details example right up here. So we want to be able to, when we do the bonding, we want to make sure that we're bonded accordingly, right? So this is an example of only 16, but most systems already deployed 32 with an OFDM carrier. We want to make sure that the config file is proper for your provisioning, as well as the upstream carriers, right? You may be having multiple upstream carriers, and some systems already started to deploy an OFDMA carrier on the upstream. And once we do the actual bonding at this point, then we can go ahead and verify the throughput. The throughput will be based on the service level, meaning that some systems have 32 and 1 OFDM carrier. Some systems have 32 and 2 OFDM carriers. So the throughput may be different for each network that you're testing. From a methodology standpoint, from a DOCSIS 3.1. All right, here's an example of this. So the objective of every technology, when we went from analog to digital, for example, we went from 64 QAM to 256 QAM. The objective was to get a bit rate that would improve the performance of the network, right? So here's an example of 6.3. This is the max rate for a 3.0 DOCSIS network. This is the max rate for a 3.1 using 4K modulation. And this is a typical bit rate for DOCSIS 3.1. So depending on the type of modulation the network may be using, most systems are deployed at 256. Some systems still have, for example, 64 QAM carriers, and that will vary. So the network will see an efficient look of 35% when utilizing DOCSIS 3.1. This will become more visible, especially for OFDM carriers that are going to be utilized on the upstream. You'll see the difference in how is it that we're using more bits per hertz in areas that we've never even used before, for example, right? So to understand an OFDM carrier, here's an example. We're going to take this frequency. For example, the carrier can be as low as 26 megahertz. It can be as high as 192 megahertz, or the bandwidth of the carrier itself. All right. So this is the low frequency. This is the upper frequency. To understand the OFDM carrier, what we're going to do is we're going to tilt the carrier. This will be the high frequency. This will be the low frequency, to understand how each individual subcarrier may be different. On a single QAM carrier, we do a single carrier that will deploy the data, for example, on a serial parallel. What we're going to do is we're going to send the data in a parallel using multiple subcarriers in this example. All right. So then again, we're going to flip this carrier, and then we're going to go ahead and look at it. So the first thing we do is we'll look at a single QAM carrier and the way we operate. All right. In this example, we're looking at could be either 64 or 256 QAMs. So as the data comes in on each individual carrier, the data is coming in a serial bit, right? A serial delivery, right? And as the data, for example, is being combined now, as we went from DOCSIS 2.0 to 3.0, we started combining carriers and started sending data, but still the carrier is sending the information on a serial, on a per carrier basis, right? So we're in North America, we use 6 megahertz. In Europe, they use an 8 megahertz carrier. So each frequency behaves independently. At least in this example, it could be either all 256, or they could be a combination of 256 and 64 QAM carriers as well. It is backwards compatible to this. But it basically is the delivery of the information, all right? So when we look at the carrier, here's an example of a single QAM carrier, for example, right? This is with Ingress, with no Ingress. This is what we want. We want it to be, to have great dynamic range. You can see the difference in an OFDM carrier, and you can see the difference on an upstream when we have a single QAM carrier and an OFDMA carrier as well with an exclusion zone. So we overlay the set-top box in this example, right? So you can see the difference between a single QAM carrier and an OFDM carrier, all right? So when we talk about the modulation and separation of every subcarrier, for example, instead of being 6 megahertz, the system can either be 25 or 50 kilohertz subcarrier spacing. Again, the bandwidth of the carrier can vary. Most systems deployed initially a 92 meg carrier, 96 meg carrier, and then they went up higher in bandwidth, but it can be all the way up to 192 megahertz. So in this example, we see how each individual subcarrier, it can have different types of modulation to carry the actual data. So in this example is really just one symbol or example of what we call one symbol in this case, or a group of subcarriers to deliver the content, and then the next carrier and the next group of carriers. As each individual subcarrier is delivering the data, it can be changing in modulation, and that modulation can possibly be between 64 and 256 QAM, 1K, 4K modulation. All right. So on this example here, looks at the spacing is set to 25 kilohertz. So it can be said most systems in North America deployed a 50 kilohertz spacing of these subcarriers. Now they could deploy at 25 kilohertz, therefore we'll have more subcarriers and therefore higher performance as well. So for right now, most systems in North America, the spacing is at 50 kilohertz. All right. The demodulation is an FFT, fast furious transfer. Based on the time, synchronization is very critical. So this is the reason why we want to verify linear distortions and those type of things that it can impact an FFT. We also want to verify code word errors. So one of the things that's going to change, instead of looking at MER and BER, for example, from code word perspective, since we're looking at so many carriers that are being deployed, as the data is being deployed, we can have ingress and noise and linear distortions and other things affecting code word errors at each group of these type of things. So we have to be able to verify code word errors across this entire symbol rate. So that changes as opposed to a single QAM carrier that can verify MER across only 6 megahertz. So here's an example of this. This will make more sense later as we go through it. When we look at a single QAM carrier, for example, we look at level MER pre and post barrier, right? But when we look at an OFDM carrier, we have to be able to look at code word errors. And code word errors start at the lower part of the frequency band. All right, so if you remember, this is the lower part of the frequency band. So if you have any ingress noise and those type of things that can impact this, and then they start to populate upward in frequency. The next code word pointer starts at the higher frequencies and populate downward, for example. So in this example, if we have noise or ingress, they can impact the ability to lock into the next code word pointer. So you have to verify this ability to look at that. So that's the reason we have the ability to look for ingress underneath the carriers themselves. All right, so this is an example of how the data is being populated. If we look at it from a subcarrier basis, we're actually demodulating the entire broadband for you to look for those types of distortions. Okay, so modulation, it can vary with an OFDM carrier, right? So we can't just basically have all of the subcarriers, basically broadcast at one time. All right, so what we do is basically stagger the information. You can see how the phase changes, for example, then. So one group of subcarriers comes in, the next group of subcarriers comes in at that point, and then the next group and the next group in order to deliver that. To make this more visible, you can see how the subcarriers are being broadcast at each individual and how, because in the world of RF, we can mix the subcarriers and produce anomalies. All of the carriers themselves are basically right at the null of each other subcarrier itself. This is very, very interesting. We don't usually do this. For those of you who've had HRC systems and those type of things, you understand from a standard or IRC network, right? So an OFDM carrier does this in order to put more subcarriers and make sure that we do not impact adjacent carriers with their data. All right, so another thing in an OFDM carrier is called what we call exclusions. All right, exclusions are sometimes what happens when we have all of the subcarriers. We may have various different anomalies. Sometimes some systems deploy an OFDM carrier in the LT band and those type of things. So you can actually have what they call exclusion zones. This is different than what we had in a single QAM carrier. right? Here's an example. Sometimes maybe you have anomalies, or maybe you have a carrier. Some systems out here in North America do have a specific channel and they can't move it, so they need to create exclusions to basically format the OFDM carrier around a specific carrier that they cannot delete because they have legacy equipment out and they cannot remove that legacy carrier itself. So exclusions are being used on the downstream, and exclusions are certainly being used on the upstream as well. So this is why I'm basically nulling the subcarriers and not sending any data on these type of carriers in order to make sure we do not affect any other services, or maybe you have excessive ingress that can be those type of things. But in most cases, it's due to a legacy carrier that is being utilized at that particular frequency. All right.
Hey, Juan, can we stop a second? We have a question that came in.
Sure.
Dave,
I didn't know if we were going to answer the questions at the end or we're going to do it now.
Well, we had a question that came in. Dave Baker, are you there? Oh, there was a...
I'll answer it. So this is Evan Natwick. We had a question from Craig Stanziano. Do you have any expectations as to when HFC plant will increase to a mid-split deployment?
You know what? That is actually being tested as we speak. Some of the major MSOs are testing mid-splits. You know, the question is that you know, if you're going to spend that much capital to upgrade the network, do you go to 85 megahertz from 42 to 85, or do you go to 200? Are you able to push out some of the legacy carriers further out? So a lot of things are going on because of the RPD deployment or DWA deployment as well, but we are discussing those scenarios with MSOs who are deploying a mid-split at 200 megahertz. Absolutely. Evan, I hope I answered the question.
Well, just, I mean, yes, people are moving to there's high split systems that we've had around forever, generally for local government and the like, but certainly to increase the upstream bandwidth that we've held with a stranglehold for years to 5 to 42 in North America. Heck, previously it was 5 to 30, 5 to 35. So people went to 5 to 40, 5 to 42. But, and that's so we can still allow people to utilize channel 2 and 3. But certainly in a closed network that we have and our ability to map out channels, we could certainly provide the same number of services in a much more regulated and smaller bandwidth. Plus, if we start to eliminate legacy boxes and go to 3.1 boxes deployed in the system, as Juan has mentioned, he's working with systems right now that are deploying nothing but DOCSIS services, meaning for legacy boxes and newer set-top boxes that because people stream their content. So, I mean, it's happening. It's happening today. So the expectation, of course, is going to be driven by consumer usage, consumer utilization, more people working out of their home from pandemic standpoint, as well as people streaming content. That just seems to be the way of the world. So it's happening. It's happening real time. It's happening now.
Thanks, Dave.
Yes, sir.
Okay, so let's go ahead and continue with the exclusions, right? Exclusions are an example, again, of removing the, not necessarily, but basically tapering down the subcarriers in order to add another carrier itself. We call this overlay, for example, right? The ability to add another carrier and wrap around. We didn't have this ability to do this on a single QAM carriers themselves. So this is a really nice example of that. So again, very uncommon, but we do have some systems in North America they decided to do this because they have a specific carrier for their legacy set-top boxes that they're unable to move. So they basically wrap the OFDM carrier around it. All right. So again, the exclusion zone can be down, 1 meg, for example, all the way up to 6 or 8 meg for European standards, etc. So that will vary. Again, here's an example of a downstream. Right, you can see how the subcarriers, this is the ONX, these are the subcarriers. So they decided to add a carrier here for the downstream. You can see the frequency on the upper and lower frequency. And here's an example of an exclusion zone. Here's an example using backtrack, and you can see the exclusion zone on the upstream. right, for the set-top boxes and how they lower that information on that. So starting very low at 5.5 to about 20 megahertz, they added an OFDMA carrier. You can see this on the ONX as well for the set-top box. Same concept as FatTrack, but using the ONX. So it certainly has happened, or is currently going on in adding this ability of adding exclusion zones. All right.
And it's probably more applicable to OFDMA and the upstream, I would say, because of all the, standard single channel QAM boxes out
there. Correct. Over time, this carrier will continue to move wider and wider on the OFDMA on the upstream. All right.
Absolutely, or timeshare.
So on this example, right, so we talk about profiles. When we do a DOCSIS test later on to Bonnie to make sure that we get that 1 gig of throughput, systems deploy different types of modulation that we talked about earlier, right? So here's just a real basic example of this. The first example is the A profile. All modems have to be able to work with the A profile as the most basic profile of all. The next example is the B profile, and then the Charlie profile, and then the Delta profile. You can see the different types of modulation that we're using. So in this real basic example, saying that the entire A profile is basically at 256. It could be 64 QAM, it could be 256, it could be 16 QAM. There's, the variations will mean. And then the B profile, the Charlie, and the Delta profile, right, can increase the bandwidth, or I should say, increase the modulation. Therefore, in the same location where you broadcast a 256 QAM, now all of a sudden it's being broadcast a 4K QAM, and this is what's changing the dynamics. We couldn't do that with a traditional single QAM carrier. We can't just go back, deploy it in a downstream 64 and go back to 256 and go back and forth. Set-top boxes and cable modems are not used to this ability, but in the OFDM world, we have this ability to switch on the fly. Each individual carrier can meet that type of modulation required. So there's a constant communication between the CMTS and the modem to see if there's any problem deploying. You can have, if my understanding, Dave, correct me if I'm wrong, you can have up to 16 profiles deliver to that. Most systems in North America deployed about 2 to 3 profiles, maybe some deploy 4, but there are variations, and that profile can vary with different types of modulation. Okay, so again, this is an example of us helping with the ONX and showing you the max modulation. We show you the A, the B profile, and we'll talk about the next cohort pointer as we go forward, right? But this is the max modulation, meaning that this is the max modulation that they're deploying at that profile, and therefore it could be lower as well. All right. Usually it's common to have the Charlie or the Delta profiles deploy 4K modulation. All right. Some systems, what they do is they increase the bandwidth of the carrier. Instead of having a 96, they'll do 110 meg, and they'll just do 2K modulation across the band and not deal with 4K, depending on the types of problems the network has in the area, etc. So there's a lot of things. There's a lot of latitude for networks to deploy various types of modulations and bandwidths and profiles. So testing the building blocks of an OFDM carrier, so we can understand which are the blocks that we need to test for, and why is it that we need to test each category. So a lot of times we all, when I'm doing these types of trainings, that people says, well, why is the PLC so important? Why is it that why isn't level and power important? Well, we'll see that the difference is because of the type of modulation that we're seeing. So the first example is the PLC, known as the 5-link channel, contains the critical information of single decoding information, right? So this is really important. If I cannot detect this carrier due to linear distortions or excessive noise at that particular frequency, I won't be able to get the rest of this upper part of the requirements, like the next code pointer, right? The next code pointer tells the modem which code words are present in which profile to find each code word coordinate. So if I was to go back a couple slides, and we were talking about all the symbols and going at each individual, all these code words are broken down into different areas. So the next code word pointer tells exactly where that group of traffic of code words are for that particular modem. So this is very, very important. The A profile is the boot profile. It's kind of like booting up your PC and identifying all of the others, kind of like keyboard and mouse, et cetera. So it's very, very important to capture this information as well. Must be able to use, so all systems must be able to use the A profile. All right. Variable bit loading is available to all of these that we talked about earlier. But the next thing is the average power and the MER and the noise. So even though we capture all of this other information, and the reason is the PLC uses a really low modulation, so it should have no problem working in most systems, unless you have excessive problems, excessive ingress, or some type of noise affecting that particular frequency. Then we get into the averaging of the carrier itself, much different than that of a single QAM carrier, because we have a lot of subcarriers to verify for you. All right, and we have to get an average MER because we're verifying the entire bandwidth, and then we're going to go ahead and verify all of the profiles for you. So this is kind of the building blocks of an OFDM carrier. So let's go ahead and talk about the first example, which is the PLC. All right, when we leave the head end, all of the OFDM carriers generally are equal in amplitude to that of a single QAM carriers, both the video and the DOCSIS carriers themselves. Okay, so some systems, what they do is they do increase the OFDM carrier by 3 dB to have better performance out in the network. Some systems, basically broadcast the carrier at equal amplitude from that of a traditional 6.4 mega carrier. So again, 2 OFDM carriers and 32 single QAM carriers is considered to be one service group, and this is the reason why eventually we're going to be able to deploy 2 gigabits of services of throughput on the downstream. The upstream is a little bit different, depending on the single QAM carriers and OFDM. But this is ultimately one service group. Now, I am working with other customers who are now deployed nothing but DOCSIS. So, and this is the reason why the ONX has multiple MAC addresses. So when I test one network, I will have to switch the MAC address and test another service group and test another service group, etc. when I'm doing my DOCSIS throughput, all right, for systems that are starting to deploy an all DOCSIS network. So again, variations across here. So we'll talk about each category. Again, the guard band, other behaviors to look at. Here's the band, the guard band, for example, right? So the guard band is up here. If we look at the carrier of an OFDM carrier, right? And then for systems that are deploy exclusion zones, you can see exactly what happens to all of the subcarriers. They drop in level. They drop not only in level, but they drop in MER and those type of things. So you may have to change your parameters for passing or failing your exclusion. If you remember, we looked at 2%. You wouldn't be able to use 2% here because of what's going on with exclusion zones, all right, those type of things. So important if using the standard on the ONX, so make sure that the settings are set for passing or failing. The PLC is it's a 0.8 dB, the higher than on the other, for example, in the carrier due to the additional pilots, so what they're saying here is that the amplitude may increase, or it is increased because of the subcarriers. If you look at, this is an example of using the ONX on the spectrum, looking at the subcarriers, you can see the amplitude. So in this portion of the spectrum, when we look at the actual power of the measurement itself, it's going to increase in power, and therefore there's a difference in power across 192 megahertz carrier. All right. From a flatness perspective, again, depending on the exclusion zones and no exclusion, those type of things, we want to verify the ICFR of the carrier itself as well, right? We verify this on a single QAM carrier, but across 192 megahertz carrier, we're taking the worst case scenario of 6 megahertz, for example, right? Or if we average the power of 1.6. So again, that's what we're looking at for right there. The worst case scenario, since we're breaking the OFDM carrier on the downstream to 6 megahertz response. All right. The next one is the PLC. All right, and the PLC, again, we break down each category. So at the very top of the DOCSIS carriers, when we select it, we see right up here, we see the frequency, the low frequency and the high frequency as well. All right, and Dave's going to show you this later. We want to verify the number of subcarriers. We want to verify the PLC. So in this case, we lock into the PLC. You can see the level. We have an independent analysis of the level. We verify the MER of the PLC, kind of like this area right up here. All right. So depending on where it can be anywhere. Usually most systems put the PLC at the lower part because they want modems to scan and detect the PLC immediately. Some systems do put it in the middle. They vary. So depending on where your PLC is across the OFDM carrier. So again, we verify correctable and uncorrectable. What we want is we want to make sure we don't get any uncorrectable, like we have this example right here on the A profile, right? So in this example, you can see the level, all right? Generally, when we're talking about a single QAM carrier, we're talking about the level of plus or minus 10. In this example, they're saying that the level should be greater than a minus 15. And the reason for that is the PLC is using a very low modulation, generally 16 QAM type of modulation. We want it to be very robust and make sure that the modem locks into the carrier in order to capture the rest of this information. So again, the level, the MER, you can see the MER is very high up here, 43. And then we want to make sure that we're locked into the status. We want to lock in and make sure that we have no uncorrectables at that point, all right? So again, just verify where that frequency is of the PLC. Verify the PLC because we're looking for noise at that particular frequency, wherever that PLC may be. The next up here, all right, is the next forward pointer. Again, the next forward pointer. We want to verify correctable and uncorrectable. Remember, if you're the next forward pointer starts at the upper part of the frequency, and they populate downward, right? Code word starts at the lower part of the frequency, and they populate upward. So again, we want to make sure that we have no uncorrectable, and we want to make sure we have a lock status. All right, because of time, again, this will vary. It's just an example of that. All right, again, we want to verify because we look at it right out here and we bring that information out again for the next cohort pointer and the PLC. And you can see the type of modulation that we're using. Very robust, right? The next one is the A profile. It's not uncommon to have correctables here, but really what we're not looking for is, or we don't want, is really any uncorrectables at this point, all right? And it can impact the A profile. To capture this is the boot profile. It's really recommended for all modems to capture that information. You could have errors. You could have errors across all the other profiles as well, and they can be corrected. All right. So again, we want to make sure that we're locked into that. The next thing we have is the level average. Since the carrier can be 192 megahertz wide, we have to average that over 6 meg. So we have a maximum, we have an average, and we have a minimum power level. All right. So again, generally the levels reckoning this is greater than -6, right? And the reason for that is that if the level starts to drop, for example, then you just like we did with a single QAM carriers, the performance will become lower, and we won't be able to meet the requirements for both level and MER in order to receive 1K or 2K or 4K type of modulation. Very, very important to have the right levels, right? If you remember the single QAM carrier, for example, can be a +10 or a -10, right? And still be able to deploy 256 QAM, right? But when it comes to this, the recommended level in order to make sure that we require the proper MER in order to deploy the proper type of modulation, all right? So whether we're in the network or in the home. All right, and again, the 2 percentile is another example of that, right? So what we do is when we look at from an MER, we look at the average across all of the, in this case, 4,996 subcarriers. We look at the deviation, right? Very low in this, and then we look at the percentile, right? Now this will be different for systems who deployed an exclusion zone. But generally what we do is we look at 98%, and then we at this with 2 percentile, we exclude at this point. So we kind of look at the best overall percent, right? So yes, that is a possibility that you could have worst case scenario. But this is because of other things such as roll-offs and exclusion zones. So in this case, you guys may have to change the percentage for systems who deployed exclusion zones within the OFDM carrier. So, all right. Other things that we want to look at is so when we want to verify the tap, the ground block, right? So if everything is working, it's just an example. If the tap is and the profiles are working accordingly, and then we move on to the ground block, and there's some type of noise or ingress or level problems, you can start to see as we go from the ground block to the CPE that we can start to go ahead and start to loose the profiles, and therefore the ability to do a throughput that is required for that customer, right? This is really no different when we do the actual network itself. So the profiles are very important to look at to make sure that we are capturing the data and make sure that we have no uncorrectable. Once we move into the uncorrectable, then the data may have to be rebroadcast again. And if you continue to do that, you may start to lose the profiles as you move from one point to the next, whether it be in the network from the tap to the ground block or the CPE. All right. So again, yeah, very quick. Green pass, red fail, right? So that's what we're looking at. Look at the PLC, look at all of the information that we just talked about, and making sure that we have no uncorrectables in order to support the different profiles for the different types of modulations. All right. Again, verify that there is no Ingress based on all the different profiles, and remember that the information, how it starts profiling from the low end frequency to the high, and from the high frequency to the lower frequency. So always look for the roll-offs and suck-outs and any Ingress affecting that particular carrier. All right. Again, here's everything that we've covered today and what's expected for each part of the building block: the PLC, the next code pointer, the profile aid, the average power, and the profiles themselves. Okay. And before I run out of time, I'm going to go ahead and I'm going to pass this on to Dave Dolnick.
Hello?
Okay. So yes, the infrastructure that's required to test the OFDM carrier, for example, right? So again, part of the service testing is to make sure that we bond, right, and look for those linear distortions. Carriers are spread out pretty broad. Sometimes they're right next to each other. So these are all verifications. Is it ready to change? Okay.
All right. Well, good afternoon, everyone. My name is Dave Dolnick. I'm a colleague of Juan's on the East Coast. And right now I have my meter up just to make sure I had signal plugged into it. So I'm going to demonstrate some of the testing capability that we have with our ONX meter today. And obviously in some of that test, we'll try and go into a little bit of detail, such as things that Juan was referring to with ingress and exclusion zones and the like, as a lot of this becomes important in how we set these profile availabilities on the different subcarriers. And I'll try to go into that in just a second here. So let me just jump out of the screen over here. I'm going to go into our channel check screen. And the reason I'm going to go into channel check is that because it's a live update, so any changes that take place dynamically while we're looking at this particular application, we'll see those real time. So the channel check and the DOCSIS check are both live measurements, meaning they update every 1 second in time, whereas the one check is a one-time snapshot, if you will. So I'm going to go into the channel check application over here. As we just verified, we had signal connected there. That's why I was looking at the spectrum. So I will launch this application over here. And like all good demos, it always takes a minute or two to start. I'm going to create a new work order ID. And today I'm just going to use something very simple like test new. All right, so I will hit enter on my meter over here to create that new job. So it clears the results of the previous measurements over here. And I will start the measurement over here on my meter. So the CPE is the wall outlet, which feeds normally my set-top box and actually a 1682 ERS router as well. David, if you have any questions, if they're pertinent, why this thing is making measurements here, I'd be happy to answer any of those.
Yeah, we have a question again from Craig Stanziano. Which attributes of the HFC is the most critical to achieving maximum throughput? Minimize trunk coaxial run lengths, limit amplifier cascades, or ingress?
Noise, ingress. everything that affects copper plants is always, it really doesn't matter truly what the payload is, whether it's analog, black and white television, or it's OFDM or whatever we come up with in the future. As long as we have an HFC plant, meaning that we have copper in the plant, we're still going to be exposed to things like radial cracks in the cable, splices that go bad, loose connection points that allow noise to backfeed and ingress into the network. And when it happens, of course, that reduces our separation of the noise floor. Ultimately, that affects the MER. And when you have reduced MER, that limits the type of services that I can deploy in that part of the spectrum. Certainly very applicable to the OFDM channel. And that's the one thing we need to think about, because as we deploy OFDM in different parts of the spectrum within our network, we have to look at the effects that those off-air service carriers may inject and create issues with quality of service. So now, looking at this live measurement over here, we're not yet at 100%, but we're looking at the OFDM carrier. We can clearly see here, it says that it starts here at 264 megahertz and goes to 360. There was a moment in time here up to literally 6 months ago, maybe even less, where the OFDM carrier was at the top part of the spectrum over here, right there in the LTE band, which unfortunately meant that a lot of people in my area simply could not get the higher level of service, that profile C that my operator uses, which is the 4K service. That provides the 1 gig capability into the subscriber's home. So there are different ways of getting around that. We certainly mentioned before the availability to create exclusion zones where we eliminate those off-air cellular carriers from being utilized by the OFDM channel. That's one way of doing it. One of the other things that's important, and this is probably even more important in the upstream of OFDMA, is the profiles that we build. When we're trying to stick in OFDMA in the upstream in between two active channels, if we're anywhere near an off-air cellular or paging provider that operates within the band of our OFDM channel on the downstream or on the OFDMA channel on the upstream, we have to limit the profiles. If we set the highest level of profiles across all the subcarriers there in the part of the spectrum where I have diminished quality of service, meaning a high noise floor, a low MER number, I cannot ever achieve those higher profiles. And that will affect what we actually see when we run throughput tests on the ONX meter. So it's always smart to make sure that we build the profiles correctly. We must always by DOCSIS spec and CableLab spec build them in ascending order. So that's the lowest profile, which requires the lowest MER. And as the MER improves, I can request those higher levels of service. If I request a higher level of service right away and I have diminished service quality, things aren't going to work, simply aren't going to work. So profile and exclusion zones are very, very important when we talk about building those properties into the CMTS. So here we're looking at the OFDM channel over here. We see the start and stop of the channel, 264 to 360. So that tells me it's a bandwidth of 96 megahertz, which is a typical bandwidth that I see here in North America. The channels are generally added in 6 megahertz blocks because we measure in 6 megahertz blocks. So if I were going to add more bandwidth to this channel, maybe go to 102 or go to 108 megahertz, that would add simply more subcarriers for me to utilize. Now, it tells me here that the PLC is at 272 megahertz. So that's basically 6 megahertz into the input of the channel. And again, an obvious reason for placing the PLC in the beginning of the channel is as we go higher in frequency, we have certainly greater attenuation on the copper part of the plant. So to make it more robust and easier for the 3.1 device to lock on to the PLC, that physical link channel, or what I like to think of as the primary link channel, because this is the frequency that all 3.1 devices must tune to come online and become active. So here we see at the PLC an extremely excellent MER here off my wall outlet after the splitter and ground block on the side of my home here, of 43 dB of MER, just really excellent. Nice low noise floor here. I will also comment that I did all the wiring internal to my home. All right. I don't know why someone keeps ringing in. I apologize. Okay. So there we see the code word error, corrected and uncorrected, or kind of pre and post, because we're all used to seeing pre and post bit error rate in the past on older signal level meters. All right. Someone seems to be insistent there, so we'll just have to disconnect the phone. Sorry about that. So, if you will, we see the pre and post there are corrected and uncorrected. And since the uncorrected is at 0, then that means that we're able to correct any errors in the pre-bit stream or prior to the low density parity checking. The next code word pointer, again, with corrected and uncorrected being at 0, again, is extremely important, because with the next code word pointer being uncorrected at 0 means that we're able to find the profiles and read them across the different subcarriers that are available. We do see that we're taking a hit on the boot profile, A profile. Although we're getting 1.8 errors per every 1,000 bits of data, we can see that the low density parity checking is correcting for those, because uncorrected for profile A is at 0. Now, the average level, max level, min level is across the entire bandwidth of the channel, including our in-channel response. Although it mentions that in-channel response is mentioned across the 6 megahertz block, where the maximum deviation is typically considered no greater than 2 dB. Excuse me. Looks like I actually have to do a hard disconnect on my phone. Sorry about that. I apologize for that. So if you will, I was talking about the average power levels across the channel over here. The in-channel response, in my opinion, at a 96 megahertz bandwidth across the channel is probably no greater than 3 dB, where 2 dB is the normal spec for a 6 megahertz channel, including the 6.4 channels coming back on the upstream. Now, average MER, again, is the average across the entire 96 megahertz bandwidth of the channel. So we're doing good. The MER, the standard deviation there, it's not bouncing up dramatically there. We saw 42.8, 43, 43.1. So we're saying that the MER is deviating by no greater than 0.6 of a dB. The maximum spec is no greater than 2. And of course, if the MER doesn't change much, we can ensure reliable services. Please remember, MER is affected by thermal noise. So as the copper part of the network heats up over the course of the day, we see those dynamic changes. That's why we currently see every couple of seconds, we'll see a change in the power level or the MER. It's simply those thermal noise changes going on in the plant, and or obviously loose connection points, ingress, as that gentleman asked about previously. So the second percentile MER at 41.8, I see it as the minimum MER, but we're saying that 98% of the carriers across that 96 megahertz passband are having an average MER of almost 42 dB. You will also clearly notice it will always be the lowest MER in this measurement here. I kind of look at it as my worst case scenario, or minimum MER. The echo is reflective energy underneath this channel, which could be caused by, again, splices that have gone bad that are reflecting energy back to me, burnt terminators and tapped faceplates, radial cracks in the cable, a burnt cable in the subscriber's wall outlet where a subscriber presses up a big heavy piece of furniture and bends the heck out of the drop cable there. You now lose your 75 ohm match from the cable and you get some reflected energy back. So the energy, the echo, has to be at least 25 dB down. dBc is decibel below carrier. So we're much greater than minus 25 dBc. The cable have spec, we're at minus 41. So some 16 dB or greater above that. So we're looking pretty good there. So these are just the physical layer measurements that we're viewing here on the ONX meter. As I page up here, since I'm looking at the OFDM channel, it is showing me, of course, the frequency and level and MER of not only my selected OFDM channel, but also the adjacent channels below me and above me. In my particular instance, as you can clearly see, the next channel above the OFDM is, in fact, my pilot channel, channel 61 and 445.25. So you'll notice that there's an open part of the spectrum here, which will explain what we see when we look at Smart Scan. But, and of course, since that's an analog pilot over there, there is no MER. So here we're looking at ingress under the channel, which is looking pretty clean over here. Let me just look at profile A. It still looks like we're taking some hits over there, so there must be some sort of reflective energy. Now remember, a spectrum analyzer is looking at the separation between the noise floor and the carrier itself. So I'm seeing the peak energy across the 96 megahertz channel. Earlier today, we were taking significant hits on profile A, but in the low part of the spectrum here, as Juan had mentioned, where normally my PLC would be, this is where we had an ingress hit. So there doesn't seem to be much of anything going on at this time, and our MERs bear that fact. So that being said, as I page up here, I see my level over time seems to be very consistent. My MER is staying within that window and always above 40 dB on the low side there, but it's varying within that 0.6 of a dB window between min and max, but always above 40, so we're looking good. So that allows me to achieve the different levels of profiles here. So let me just explain what's going on here when we look at profile analysis. We can clearly see that the PLC and the next code word pointer are both at QAM 16, and that's because I can sustain 10 dB higher noise floor at those lower QAM modulation rates and still be able to lock onto the carriers. As I need to be able to lock onto the PLC to be able to even decode the OFDM channel itself, this is extremely important. Then in my particular network here, we have our profile A, B, and C in ascending order, as is required for the boxes and devices to work correctly, both in the field and for the meter itself, which has a 3.1 modem. So QAM 256 running at roughly 39 megabits per second, 1024, which can achieve data rates of somewhere around 600 megabits per second, 4096 or QAM 4K can actually do up to 2.2 gigs if so configured. Typically, we use that as our 1.2 guideline, 1.2 gig down guideline or testing service for the 1 gig service we provide to our customers today. And as Juan had mentioned, we can certainly bond OFDM channels together to dramatically improve that bandwidth into the subscriber's home network. So if we look over here, we see that we have a green lock light on the PLC, the next code word pointer, and profile A. Yet I see the word yes highlighted for profile B and C, but there is no green light on them. And the reason why is there is no threshold currently selected for those profiles. The cable app spec requires that profile A be measured as a quality matrix, but there's none required for the additional profiles. And I suspect that's because it's up to the provider to determine how he's going to layer this out. A profile A at 256, profile B maybe a QAM 512, a 1024, a 2056, a 4096. So it really depends on what service levels that the operator wants to provide and layers of tiers of service to their customer base. So adding new revenue streams. So profile analysis is very important. So again, I am locked on profile B and C. And what's important to understand here is my meter is not provisioned for this network. So the fact that I see profile C there is not reliant on my meter being provisioned for the 1 gig service. It just simply shows me that in my common distribution path, I have devices pulling the 1 gig service or the profile C. So since I'm on a common distribution point, I can see the reflection of that. So since it's an active service, someone's pulling down that profile on my distribution path over here. So what am I looking at here? In profile A, prior to error correction, I have 1.8 errors per every 1,000, 8.9 for profile B for every 100 bits of data, 7.6 errors for every 10 bits of data. In profile C, certainly QAM 256 starts having errors when you start falling below 1.0 e to the minus 6. So this is a lot more reliable and a lot more robust error correction than we ever had in traditional broadcast QAM single channel services. So the idea here, 7.7 errors out of every 10 bits, but error correction is fixing that. So I can certainly provide that 1 gig service. Now, how do I use this profile analysis to determine where I have issues? If I cannot pull that profile C at my wall outlet over here, as an installer, I would certainly go to the output of the ground block to see if all the profiles are coming through the ground block that may have been sitting on the side of the home for a period of time. If I don't see all the profiles there, I would look at the end of the drop cable feeding that demarcation point to see if all the profiles are available there. And if I don't see all the profiles there, I would certainly want to go to the distribution point, that distribution tab, and pray that they're all available there. And if I see them there, It's a matter of probably running a new drop cable to that ground block, making sure all the profiles are then available, plugging through the old ground block, make sure the profiles are still there. If not, you're going to change out the ground block and move on from there. So we're isolating each part of the network. This is also true for the plant person, the person that works in the outside network. At the node itself, I want to make sure all the profiles are available on every distribution leg. And if all the profiles are there and I can go to the termination point of that distribution leg, then any other loss of profile has to be related to the drop plane itself. But remember, if I go from the optical node itself to the next RF active in cascade, I see all my profiles there. I move downstream to the next RF active, I'm missing a profile, like profile C. I simply start backing up the network itself to the passive device before me. Are my profiles A, B, and C there? No, let me move up to the tap before me. Gosh, well, they're all here. So what's in between those two tap plates? A radial cracker 3, a splice that's gone bad? That's what we're looking for. So that's how we use profile analysis to determine where we have issues in the network. Now, one of the things I do see here, which is problematic from my standpoint, is the fact that we're taking hits on the code word errors corrected. So prior to error correction, certainly if I'm the plant person and I'm plugging into an optical node and I see these tremendous number of errors out of every 10, that's bad news bears. So for me, the first thing I would do is I would remove the fiber jumper. I would then clean both the bulkhead connector and the fiber jumper and then visually inspect it with a microscope to verify that it meets IEC standard and is clean. And if I can verify that and prove that by taking snapshots in my meter, and I still see errors there, then that means that at the other end, at the transmitter end, we need to clean the fiber jumper into the laser transmitter and the bulkhead connector there to improve quality of service. We want to minimize the amount of energy that we see over here or code word errors prior to converting to RF and distributing on the copper part of the plant. It's only going to get worse from there because we're exposed to inductive energy. So if we don't have good numbers at the node, it can only go downhill from there. We must ensure that we have good service quality both at the optical distribution point where we convert to RF for HFC distribution, as well as making sure it absolutely is correct when we input it into our network. So that means that sometimes we have to clean the fiber shelves and the input to the laser transmitters at those remote head ends or hub locations. So very important concept to understand there. The in-channel frequency response, why it appears to be a rocky road, the delta between this low point over here and this high point here is only half of dB. Again, we're looking to be hopefully within a 3 dB window or 2 dB delta to make sure we're seeing flatness here. Now, the rocky road that we're seeing here is simply every 128 subcarriers here, we kind of raise the gain of those subcarriers there as file pointers to make it easier for the 3.1 device to move between those different segments of the network itself, of that OFDM carrier. Okay, so let us move along here. Okay, so so these are just different things. A smart scan, again, MER across all the channels, our favorite channel data, but it's really the profile data analysis and the physical data that are important for the meter itself. The other thing, while we're on this, on the meter itself, I want to bring up over here, but I'll have to move to a different port, is looking at Ingress Expert. And the reason why we do this is because we may, in fact, have an OFDMA carrier on the network, although at this moment in time, it is not being utilized, meaning it is being tested, but it is being time shared. It's not bonded as an active service to the upstream channels at this point in time. So I'll see if I can explain what's going on over here. Let me just push up over here on my display. So one thing, I ran a DOCSIS test prior to our meeting, and we can clearly see that they're running 4 upstream channels over here. And I'll show you here in the Ingress Expert mode, OFDMA running, but it's not an active bonded service. If it were an active bonded service, I would see that as one of the upstream channels here. Now, what I'm trying to demonstrate here is that if it becomes an active service, I will be able to track the upstream SNR as well. This is an important concept because the profiles that I configure in the OFDMA channel are going to be based upon the SNRs that are available on the network. So it's important to maintain a nice tight network. By the way, this of course is how we can determine which particular leg, if we have a node health issue, we can determine which leg has the highest noise contribution by plugging into each P leg in the node itself, and very quickly finding out who has the lowest SNR. So I do not have to pull the return pads and kill the upstream service. So the availability to be able to track the real-time traffic up on the network itself to show diminished MER is how I track noise and improve the service quality in the network. Again, I don't have to ever pull the return pad, so I don't have to kill the actual upstream services. Now, as we look over here, let me try and pull this spectrum down over here. We certainly see the DOCSIS 3.1 services over here. And it looks like OFDMA is not turned on at the moment here. I do apologize for that. We may see it blink on over here, and you'll see it cover across all the entire upstream over here. Well, I don't see it happening right now. Let me just see one thing, if I can get a closer image of this. Nope, I'm sorry. So OFDMA is not operating. It was up this morning for a session I did. One thing is I do have heat mapping turned on, so it makes this beat here at 22.3 very, very visible. That's the idea of heat mapping. So it makes beats discernibly visible in the return spectrum over here. All right, let me drop off over here and let me bring up Expert Track. Now, in our Expert Track server, we have the ability with Expert Track to also monitor the DOCSIS 3.1 services coming back as well. So the idea here is that we're looking at node health, if you will, to the best quality nodes, to the worst quality return paths coming back on the network over here. So if I plug in, click on any particular node that shows a load node health score over here, I can isolate what's going on in the 3.1 world over here. So what I see going on right now over here when I look at 3.1 is that I'm able to achieve profile A and profile C. So if I know that there's a profile B, I would certainly expect to see its presence there. But again, depending on how I set those profiles up for those subcarriers, that profile B may be segmented to a part of the carrier there where I have a high noise content. So I'm seeing the presence of, in the 3.1 world, the profile 3.1 boxes over here. So I can certainly click on this and try and do a little bit better isolation as to who 3.1 is amongst all the modems in the path over here, as opposed to just looking at the node itself. So this is just some of the information I'm able to bring back over here. So let's see if we can find a node that has more 3.1 boxes on there. So here, profile A, profile B, no profile C. That's problematic, right? Because we want to see our 1 gig service with that profile C over there. So only profile A seems to be working, and we have profile B over here. He seems to be hidden. Select this. I don't see that gray box, but it must be sitting behind one of these. So the idea here is to show that profile. So let's move back once again. Let's look across some other paths over here. The 3.1, 3.0. Whoa, I don't know. That put me into the way wrong area over there. Modems by profile. All right, so that's apparently looking at a node somewhere out of this country, Republic of Congo. So Expert Track is a far-reaching system. I suspect that's not one we want to look at. Let's look at a CDR, all right? Cisco path over here. All right, so I see, okay, the different profiles over here. So we're able to track a little bit more information. And the idea here is that if we have an expert track system and we have RPM 3000 cards or the HCU 200s, we're able to look at the OFDM carriers coming back and look at the profiles that are available on the upstream ports of the expert track or the path track system itself. And certainly, even if I go into the node information over here, I do have the availability to look to see what may be causing interference by looking at different things, such as an example, heat mapping over here. Let's see if we have ingress underneath the channels over here that may be causing issues with quality of service. Well, actually, I'm not seeing any service on this particular return path over here. Let's choose a better node. So let's just see what's going on here from a spectral viewpoint. I'll just look at the heat map. So there I see my 4 upstream carriers. There is a slight buildup in the return band over here, probably related to a bit of drop noise, maybe an out-of-band set-top box firing over here. But again, the idea here is to see this buildup of beats or in-band ingress over here. So this is, again, my noise floor and my heat map. So actually that's looking pretty good. We see a lot of active energy here on these 2 channels over here. That's why we see the higher coloration. It's just more activity or more energy there. So more active traffic being moved to those individual upstream carriers here. So just some of the information we're able to see here. And just looking at the spectrum over here, we'll just take a quick look at that. So I'll turn on all my different applications, min, max, hold, and average data. And for those of us that are used to using ONX meters, this will probably make a whole lot more sense to you. So when we look at Ingress scans, I just had on my or Ingress expert mode. So in fact, I can just turn off the heat map over there and just bring it up so it looks more like what we would tend to see over here. But average power level. So what we're looking at over here under average, when I turn on average, so I would expect to see energy here underneath the active service channels over here. What I also notice is out of band, my min energy and my average power level over here seem to be nice and low. A little bit of buildup over here, probably related to a little bit of drop noise. This is important to me as a plant person to be able to determine whether or not I have a plant-related issue or an install-related issue. This may make a little bit more sense for those people that are used to using the ONX meter, looking at noise. So if you look over here, and let me just move my pan button back out over here. Again, we see the same type of scenario over here. I see, and we just see active traffic over here, but the green or the average power level was nice and low. And that happens when you have nice tight connections behind the subscriber device. So you may see that in band, the average power level may drop considerably. And that's when the device has a nice tight connection on the back of it, at the wall plate, at the barrel behind the wall plate, the ground block, the jumper from the ground block to the distribution tap itself. If everything is nice and tight, I can have active energy, but my noise for my average power level stays low. So please understand that this is a contribution of all the active traffic coming back up the network. But what I do see is out of band, my noise force seems to be fairly low. Now this was a impulse pay-per-view set-top box that fired, but when he's not firing, I do see a little contribution of drop noise down over here. Closer to 1 megahertz. We scan from 500 kilohertz out on up over here. So again, what I'm looking over here is to determine, is all my average power level raised in the active upstream channels? Is there an out of band, like a bad splice, a radial crack? Because if I had that, then the average power level would come up as well out of band. So this helps me isolate, which is why I'm looking past 5 to 42. I'm looking at like 65 megahertz. So I can view out of band to see what out of band power is going on in the min over there. And that's why I relate this to what we see over here. That's why I look on at average power here as well. So those are just some of the tools that we have in PathTrack along with our ONX meter to be able to look at different scenarios within the network. That's really all I have on my end at this point. Okay, so I just need to stop sharing my screen. There we go.
Are you able to see the screen? Okay. Well, we want to thank everyone for supporting today's presentation. Here's the information on our customer service, technical support. Is there anything else you need to add to this, Dave?
No, I just want to thank everyone for attending. I hope they found it beneficial. Juan, thank you so much as always for going to the
Do we have any questions from the audience that are pending? Okay. Yeah. If there's any questions that you have and anything we've covered, both on my end or Dave's, Dave, let me know. If you can please respond to the chart.
Absolutely.
We're going to post our email address and our technical support information as well, so you can contact us for any further information. All right, everyone. Again, my name is Juan Castro, and I want to thank everyone for joining.
My name is Dave Dolnick from VIAVI Solutions. And again, I want to thank you all for joining us today on our YouTube live stream presentation. Thank you so much.